In our modern age, it is vitally important that our students get a solid grounding in mathematics and science. A computing calculator designed for use in high school classrooms has created tremendous excitement among educators. It is capable of helping the student understand many math and science concepts in greater detail and with more speed than ever thought possible. The computing calculator illustrates these concepts in a new and challenging fashion, and yet it provides the opportunity for individual study. Calculating devices do not eliminate learning. They only do what they are told. Students must completely understand the logic of problem solving and be able to provide a correct set of instructions. In addition to classroom work where the whole class participates, a computing calculator makes an important contribution to individual learning. It has long been known that things which we discover for ourselves are the things which we retain the best. The classroom calculator is made to order for enrichment assignments. This enrichment can be provided with minimum demands upon the teacher's time which is now utilized to give students individual attention.
The heart of the classroom system is the 9100 computing calculator. It can be used as either a very simple to operate calculator or a very powerful desktop computer. It is a completely self-contained unit made up of a keyboard, a cathode ray tube, and within the case, the electronics package. In the center of the keyboard are the arithmetic, operation, and numeric entry keys. As I enter numbers on the keyboard and touch the appropriate key, decimally correct results instantaneously appear in the cathode ray tube. A large screen display, which duplicates the contents of the cathode ray tube, can also be used for classroom participation. Also available is an electronic printer, which mounts directly on top of the computing calculator and will permanently record entries and answers. To the left of the numeric keyboard are a group of keys used for the storage of intermediate results and constants. And for students of trigonometry, analytic geometry, calculus, biology, chemistry, and physics are a group of keys that automatically provide the trigonometric and logarithmic functions so often used in the advanced mathematics and the sciences. The 9100 can also be programmed to remember repetitive operations. As an example, I will create a program to solve the quadratic equation y equals x squared plus 2x minus 5 for various values of x. I simply set the switch to program and key in the steps appropriate to the solution of the equation. By setting the switch back to run, the 9100 is now ready to solve the equation for any value of x that I may select. If I enter 10 on the keyboard and touch the continue key, I execute my program and display the corresponding value of y. This procedure can be repeated innumerable times, and a table of y values can be built describing the particular function. If the program were one that I wish to save for later use, it can be recorded permanently on a magnetic card, simply by entering the card and touching the record button. Now the program is permanently stored and can be reused at a later date. For graphical representation of solutions, an XY plotter is also available. Let's take a look at a plot of the same problem, y equals x squared plus 2x minus 5. On this magnetic card, I have already recorded the program to compute, graphically plot, and permanently record the solutions to this equation. Let's enter the program and observe the XY plotter and electronic printer in operation. Solutions to problems can be programmed at home by students using cards that are marked with a pencil with codes representing instructions. When a card is run through a reader, it programs the computer in the same manner as done with a magnetic card. This allows freeing of the computer for greater utilization by a number of students. For example, students can check their homework assignments before class. Others can do special problems on their own for greater enrichment. Teachers can quickly recognize which students require special attention. Let's take what might be a typical example of a student exploring an experiment in the sciences. To determine the multiplicity of bacteria in a pure nutrient solution, the exponential function n equals n sub 0 times 2 to the kt is used where n sub 0 equals the original amount of bacteria, k is a constant relating to the kind of bacteria, the time, and the nutrient, and t is the measure of time. Using a MarkSense card, the student programs the computer and inaugurates the program. As the computations are performed, the numerical data is printed and a plot representing the increase of bacteria per unit of time is graphically described on the chart. When the experiment is completed, the numerical data printed on the tape goes along with the chart. The 9100 classroom computing system is being used by many schools with remarkable results in subject matter comprehension and reasoning skills. In the 70s, it is truly a tool for intuitive learning.
At more advanced levels, the computer and plotter provide teaching aids never before possible. Easy to understand simulations of complex phenomena are available for all students. Now let's watch a physics class using the more advanced capabilities of this system.
Okay, now today we'd like to go back and put together the things that we've been learning. We've talked about a body in linear motion. And we know that we calculate the distance that that body moves by multiplying its velocity times its time, which of course is the same sort of thing you do every time you calculate how far you've driven in an automobile. So that the horizontal distance is equal to the velocity times the time. Then we spend some time discussing what happens to a body when it falls, just in a straight line. And again, it's moving in a straight line, but its velocity is increasing. It's going faster and faster all the time. And we developed the equations for that. If we have zero initial vertical velocity, the vertical distance y equals the initial displacement y0 minus 1/2 the gravitational constant times time squared. What we'd like to do this morning is to put these two ideas together and study what happens to a body when it does something like this, where it rolls off a table and starts falling. When it's on the table to start with, it has a pure horizontal velocity. So we have the first case. When it goes over the edge of the table, it has both a horizontal velocity and a vertical velocity. We're going to put those together. Now, when I roll the ball like this, it all happens pretty fast. It's pretty difficult to see moment by moment exactly what's happening. So what we'd like to do is to slow that action down, and we're going to do that by using the computer that we have here and ask it to draw a graph of the path that the ball would take as it comes over the table edge. I have the program in that uses these equations to calculate the position of the ball, and I've marked the initial conditions down here on this optical card. So let me put those in, start the program going. Then you'll notice that the plotter started off with the ball going almost straight out, and that as longer that the ball is falling, the more it starts moving in the down direction this way. You'll notice one other thing that you didn't see when we did the real thing, and that is that we have little timing marks on here. These little dots are exactly 1 second apart, so that we now have a clock that's superimposed on the motion of the body, and we can actually time what happens from moment to moment as the ball comes down until it heads toward the ground. While that plot is finishing up, I'd like to pass out some copies of that same plot that I made up before class. Barb, would you take those for me? If you'll pass those around, and then we'll see what kind of an analysis we can get from this calibrated plot. See, the ball is just about to hit ground down here, and the computer is programmed to come back up to the top of the table. Let me turn this thing off now, and I'll move the pin out of the way so that we can see what's going on. And you can follow along with the graphs that you have and do exactly the same thing. What we would like to do now is to find some way of calculating the length of this curved arc. We've been calculating the distance that that body travels, and now we'd like to calculate the distance along a curved path. And one way we could do that would be to draw straight lines between successive dots, something like this. Okay, and we could do that between each successive dot and use these straight lines as an approximation to the path of the curve. So why don't you do that for 1 or 2 values? We could, of course, count the squares along the diagonal line, but they cut across squares. It's kind of hard to do. And so an easier way to do that would be to break it up into its vertical and horizontal components so that we have the vector resolve into its vertical component and its horizontal component. Now why don't we step over to the blackboard here, and we'll see just exactly how we can use that. If we draw the vector that approximates the curve, we break it up into a vertical component and a horizontal component. Let's put a number of labels on these so we'll have something to talk about. We'll call this one delta y, and we'll call the horizontal component delta x, the change in the x distance, change in the y distance, and we'll call this one delta s. Okay, now if we have equations that calculate x and y for us, we can calculate the difference in x and the difference in y. If we know those, how do we find the distance of the hypotenuse of that triangle? Joy, what could we do to find the distance of that hypotenuse?
Use the Pythagorean theorem.
Use the Pythagorean theorem. Okay, what's the Pythagorean theorem?
X squared plus y squared equals s squared.
S squared equal delta x squared plus delta y squared, but we don't really want delta s squared, do we? What do we do to do that?
Take the square root
Take
of
the
both
square root of
sides.
both sides, okay? And real rapid square root like that will just erase it off. Okay, so we could take the square root. We can go back now to our calibrated graph, and all we need to do then is count these squares, and we know that each major division here is 100 feet. Count horizontal squares at 100 feet per inch. And to calculate the square root of the sum of the squares, and then do that successively. Let me draw another one in here, like that. Okay. Randy, how much time is that going to take you to calculate all those arc segments?
It'll take a while.
Take a while, won't it? How good is our approximation? Is the approximation by adding up those line segments, does it come close to the arc length? Diane, what do you think?
It comes close, but it would never be the same.
Won't be the same. Why do you think it's not going to be the same?
Because the curved lines are going to be longer.
The curved line's always going to be longer. Is that right, Joy? Is a curved line always going to be longer?
Yeah.
Yeah, the curved line's always going to be longer. Okay, so we have an approximation. What can we do to improve the approximation? Anybody got any ideas? Randy?
Well, what if we shorten the triangle there?
Okay, we could put in more dots, couldn't we? Divide this up into 2 small triangles like this, okay, such that each curve each little line segment more closely approach the curve. What does that do to the amount of calculating work you have to do?
Well, it just doubles it.
Doubles it at least, doesn't it? Okay. Suppose I ask you to divide that up into 100 pieces. What does that do to the approximation?
Well, it makes it quite a bit more exact.
And Randy, how about the amount of work involved?
It's going to do more than double it.
It's a lot of work, isn't it? Well, computers are just great for doing that. We know exactly what we want it to do. We just want to calculate these arc segments. And since we've got so much calculating power, we're going to ask it to do one more thing. What happens if we define this to be 0 degrees, and we define this down here to be 90 degrees? What happens to the angle, this angle right in there, that the resultant vector makes? Let's see, let me define it as this angle up there, okay? What happens to this angle in each succeeding time interval? Anybody else? Yeah, Joy?
You get a bigger angle.
You get a bigger angle, don't you? The longer the ball falls, the more that vector tends to tilt down, so that the angle should start at what?
0.
Should start at 0 right after it comes off the table. And if we let this thing run, say, below ground, you know, like for several minutes, what's going to happen to the angle?
It'll be 90 degrees.
It's going to get close to 90 degrees. Well, let's see if that's really true. Let's put a program to do just exactly that into the calculator. I have such a program here on the magnetic card. We'll put the program in the computing calculator, and then let's put in the same set of initial conditions that we were using over here on the graph. That is to say, we'll start out with an initial horizontal velocity of 100 feet per second, and I'll put that down in the Z register. We'll put in the height that we start out with, our big high table there, 800 feet, and we'll start out with 1 second increments. Okay, so there we see it on the display over here, all loaded up. Let's start the continue, and you'll notice on the display that we are counting up in seconds here in the bottom register. Whoops, it's all through already. There's the path length, 1102.79, and we didn't have quite enough time to talk about the angle that we saw. Let's write that down. For a time increment of 1 second, we get to what? 110279. What's going to happen if I put in twice as many increments, or make each increment half as big, say half a second like that? Is this number going to get bigger, or is it going to get smaller? Yeah.
It should get bigger.
It's going to get bigger. Why is it going to get bigger? Diane's got the answer. She just...
Because it's going to be more like the curve.
It's going to be more like the curve, isn't it? Okay, let's try that. We'll put in half a second and see whether that works. We'll start over here, put in the same 100 feet per second that we started out with, put in a table of 800 feet high, and we'll put in 0.5 this time down in the bottom register, and we'll start the program off. Now, it'll take a little longer this time. You can see it's counting up by half-second increments instead of by 1. Here's the distance that the ball is traveling, building up. Here's the angle. Just went away. Okay, 1103.71, and sure enough, you're right, 1103.71. So it gets a little bit larger. How do you feel about the change? Really, it doesn't make too much difference, does it? Because we're talking about 1 foot out of 1,000 feet. And what would happen if we put in 100 increments? Would this number get bigger or smaller?
Bigger, but not much.
Get a little bit, not an awful lot bigger, would it? Okay, well, you might like to try running some of these yourself, so why don't we pass out some of the Mark Sense cards, if you'd pass those around, and go ahead and you can, yeah, you have a question?
Yeah, if you put in that magnetic card, then can you put in any height that you want?
Yeah, the program will accept any height. Now, we put in the same ones that we used on the plotter over here to make them agree.
But you don't have to change the card?
Don't have to change the magnetic card at all. You can put in any set of initial conditions that you want. Any of you that have problems marking up your cards, why, sing out and we'll see if we can give you a hand at it.
In addition to mathematics, algebra, and physics, the classroom calculator system has many useful applications in chemistry, biology, and economics. The calculating power and the wide range of versatile accessories which you have seen is available for your students at a very reasonable cost. Basic equipment costs for the calculator and card reader, amortized over 5 years, when divided by the number of programs per year, using a school year of 180 days and actual classroom experience of 26 programs per hour, result in the low cost of less than 5 cents per program. The availability of computing calculators small enough and inexpensive enough for classroom use has opened up exciting possibilities in creative teaching. Forward-looking educators are carefully studying these opportunities. For additional information, write Hewlett-Packard, Post Office Box 301, Loveland, Colorado 80537, or contact one of the more than 125 Hewlett-Packard offices conveniently located to serve you in major cities around the world.